The world's tallest skyscraper was never expected to remain perfectly motionless. When structural engineers designed the 828-meter Burj Khalifa, they completely anticipated that the immense weight of the structure would compress the earth beneath it. But here is the counterintuitive fact that defines modern super-tall engineering. Downward movement alone does not mean a skyscraper is failing. A tower can settle into the ground and still be behaving exactly as its designers intended. The real danger is something much more destructive. Imagine two completely different physical scenarios. In the first scenario, the entire massive foundation moves downward in a reasonably uniform way. The building simply changes elevation, remaining perfectly upright and secure. Now imagine the second scenario. One part of the foundation sinks slightly farther than another. The structure is no longer just moving downward. It is being violently forced out of its intended geometry. A modern skyscraper can survive downward movement far better than it can tolerate unexpected physical distortion. So how do engineers make an 828-meter megastructure settle predictably instead of allowing one side to sink faster than another? To answer that question, we have to separate what a tourist standing on the sidewalk sees from what a geotechnical engineer actually measures. When most people hear the word sinking, they immediately picture a catastrophe. They imagine a building losing its battle with gravity, leaning dangerously over the city, and heading toward inevitable collapse. But in the field of geotechnical engineering, settlement is an accepted physical reality. Enormous structural loads will always compress the ground beneath them. The engineering issue is not whether the building will move, but exactly how it will move. This brings us to the fundamental difference between uniform settlement and differential settlement. Think of a simple four-legged table resting on a soft surface. If you push down evenly and all four legs sink into the ground by the exact same amount, the tabletop remains perfectly level. The entire physical system has moved downward broadly together. But if only one leg sinks deeper than the rest, the table immediately begins to tilt. The physical geometry is instantly compromised. Now, scale that simple table up to an 828-meter skyscraper. A super-tall tower is a highly complex, deeply interconnected physical system. It is a massive network of load-bearing columns, rigid concrete walls, delicate glass facades, high-speed elevator shafts, and thousands of internal joints. All of these physical components must continue interacting correctly under extreme pressure. If different parts of the foundation begin moving relative to one another, that internal geometry is forced to distort. The engineering problem is not merely asking how far the building moved in total millimeters. The critical question is whether different parts moved in the way the engineers explicitly expected them to. To predict that movement, engineers first had to understand something much less glamorous than the towering glass facade of the Burj itself. They had to deeply investigate the complicated ground underneath it. It is a common misconception that Dubai's skyscrapers simply sit on deep dunes of loose desert sand. The reality of the geological environment is far more complex. The published engineering literature for the Burj Khalifa describes a highly stratified subsurface. What looks like one solid, uniform surface from above is actually a densely layered geological system. Beneath the surface sand lies a sequence of marine deposits, much weaker materials, and distinct layers of carbonate rock, whose physical properties vary significantly with depth. In structural engineering, this physical variation matters immensely. Different geological materials compress and transfer enormous vertical loads differently. A solid layer of carbonate rock will not compress exactly like a weaker layer of marine deposits when subjected to the concentrated weight of a megastructure. If the ground beneath a building is perfectly uniform, predicting settlement is a relatively straightforward mathematical exercise. But when the ground consists of multiple distinct layers with differing stiffness and bearing capacities, the risk of differential movement naturally increases. Engineers must carefully calculate how each distinct geological layer will compress under highly specific structural loads. They cannot change the local geology, so they must design a way to control how the building interacts with it. If the ground is not one perfectly uniform block of mythical bedrock, How do engineers make a tower of unprecedented scale behave predictably? The answer lies hidden roughly 50 meters below the surface. To control how the Burj Khalifa interacts with this extremely complex geology, engineers designed a massive foundation system known as a piled raft. It is simply not enough for a tower this heavy to stand directly on the surface. The immense structural load must be intentionally distributed deep into the stronger geological layers below. The physical system begins with the raft itself. This is a solid, heavily reinforced concrete mat that is approximately 3.7 meters thick. On its own, this enormous solid slab helps to spread the weight of the entire tower over a much wider area, drastically reducing the pressure on any single point in the soil. But the raft alone is not enough to control settlement in this specific geological environment. Beneath the concrete raft, engineers installed a massive network of bored piles. These solid concrete cylinders are approximately 1.5 meters in diameter and extend roughly 50 meters beneath the base of the raft. They reach deep into the layered carbonate soils and rocks, anchoring the structure. But there is an important physical revelation here about how these deep piles actually work in practice. They are not simply enormous stilts resting on one mythical, unbreakable layer of perfect bedrock. In fact, a significant portion of the foundation's strength comes from a mechanism called skin friction. As the immense weight of the tower pushes the concrete piles downward, the surrounding soil and rock press tightly against the outer sides of the piles. Much of a pile's ability to carry the vertical load is generated by the enormous amount of physical contact and friction along its entire vertical surface. The thick raft and the deep piles work together as one highly integrated, unified system. They distribute the massive vertical loads, anchor the tower against severe lateral forces, and heavily restrict how much the ground below can actually compress. However, this brings us to a harsh reality of basic physics. A gigantic, deeply engineered foundation system is incredibly effective at distributing load and minimizing overall movement. But it cannot completely abolish the fundamental physics of settlement. The ground will still compress under hundreds of thousands of tons of concrete and steel. The building will still move downward over time, and the structural threat of unexpected distortion remains present. The geological reality beneath the Burj Khalifa is incredibly complex, but the real engineering challenge begins when that deformable ground continuously interacts with the rigid structure above. Earlier, we looked at how the piled raft foundation distributes weight. Now, imagine a visual thought experiment tracking that foundation over a period of time. In version 1, all major parts of the foundation move similarly downward. The entire structure settles by a few predicted centimeters, and the building simply sits slightly lower in the earth. In version 2, one wing of the massive structure moves noticeably differently than the central core. The audience should physically feel the immense difference between these two outcomes. Uniform settlement mostly changes a building's overall elevation. Differential settlement can actively begin changing its physical shape. Ground movement dictates foundation movement, and when different parts of the foundation move unevenly, different parts of the superstructure are violently forced to respond differently to the new stress. The physical geometry of the building is literally forced out of precise alignment. The columns that carry the main load could experience twisting forces they were never meant to handle. Internal joints, delicate glass facades, and non-structural elements may experience additional, unintended deformation. If this physical chain reaction becomes severe enough, structural concerns can rapidly develop. This is a primary failure mechanism that geotechnical engineers aggressively design against, and they must anticipate these forces long before construction begins. So, after all the theoretical models and calculations, did the actual Burj Khalifa behave the way its engineers predicted? This is where the story of the world's tallest building takes a surprising turn. Given the extreme height and the challenging geological layers, it is easy to assume the structure is constantly fighting a losing battle against the Earth. But the published engineering work tells a completely different story. Engineers meticulously compared the predicted foundation behavior with the actual measured settlement during the entire construction process. Later structural monitoring work explicitly reported a strong agreement between the actual measured settlement and the original analytical predictions, especially given the immense complexity of the project. This core narrative reversal is highly important to understand. The Burj Khalifa is not an example of a skyscraper losing its battle with the ground. It is the absolute highest example of exactly how much rigorous work goes into preventing that battle from ever becoming visible. Engineers mathematically modeled the expected movement, physically measured the real tower as it gained weight, and strictly compared their early predictions with physical reality. The actual observed behavior matched the engineering models with incredible precision. By thoroughly understanding the exact physical properties of the carbonate rock and marine deposits, they accommodated differential settlement before it could start. The structural integrity of the tower was never compromised by the ground acting unpredictably. The unsettling part of skyscraper engineering is not that a massive building moves. The truly unsettling part would be a physical movement that the engineers simply did not expect. The careful monitoring of the Burj Khalifa proves that downward movement can be safely controlled. But downtown Dubai is not the only foundation environment in the rapidly expanding city. In other highly developed areas, Dubai is not just building on layered natural ground. It is dealing with a foundation environment that is entirely manufactured. Across the extensive coastline, developers create massive areas of newly reclaimed land. A prime example is deeply documented in the geotechnical case study for Pearl Jumeirah, an artificial offshore land formation. This massive project was built from reclaimed sand and rock fill. Across the site, the depth of this reclamation fill was typically on the order of 10 to 15 meters. First, Dubai literally creates the land by dredging and placing millions of cubic meters of material into the ocean. But you cannot simply build a heavy structure on loose, freshly dumped sand. Before any vertical construction can begin, engineers must systematically compact the new earth. They use highly specialized ground improvement techniques, including heavy vibro-compaction and surface compaction, to force the loose sand particles tightly together. Then, they meticulously test the resulting density. Engineers physically investigate the bearing capacity of the newly formed ground and carefully evaluate the liquefaction risk. Finally, after all of this preparation, they ask that engineered ground to support massive infrastructure and dense residential buildings. This introduces a completely different dynamic than building on natural bedrock. When you build a tower in a downtown environment, you are dealing with millions of years of natural geological formation. When you build on reclaimed land, you are relying on ground that was engineered into existence over a period of mere months. The underlying engineering question shifts. How do you accurately predict future movement when part of the ground itself was manufactured? This does not mean that reclaimed land automatically sinks dangerously or that offshore islands are destined to fail. It simply means that the geotechnical engineers face a much more complex set of physical variables. They must account for the initial settling of the artificial fill material while simultaneously predicting how the deeper, natural seabed will react to the added weight. Every single mathematical calculation must be incredibly precise, and this specific challenge brings us back to the smallest, yet most important thing in the entire story. It brings us back to physical movement that might be almost completely invisible to the human eye. Exactly how many millimeters of structural movement are actually dangerous? It is the most common question asked about sinking cities, and we must deliberately reject an oversimplified answer. There is absolutely no single, universal number of millimeters that means every skyscraper has suddenly become unsafe. Geotechnical risk depends on a highly complex combination of specific physical factors. It depends heavily on the unique physical geometry of the building. It depends on the structural stiffness of the core, the specific foundation configuration, and the precise distribution of the vertical load. A flexible, lightweight steel structure might easily tolerate a level of differential settlement that would cause catastrophic cracking in a heavy, highly rigid concrete tower. Furthermore, the overall rate and pattern of movement matter far more than one isolated measurement. Engineers are intensely focused on the strict design tolerances of the individual building elements. They are often far more interested in the emerging pattern than in one dramatic number published in a headline. The questions that actually matter narratively and scientifically are extremely specific. Is the ground movement broadly uniform across the entire site? Is the settlement continuing at a steady rate, or is it safely slowing down as the ground fully compresses? Does the physical reality completely match the analytically predicted behavior? Is one specific location of the foundation suddenly diverging from all the others? The viewer must learn one fundamental truth about modern structural monitoring. The engineering problem is not simply measuring settlement. The true problem is detecting the exact moment when physical reality begins separating from the mathematical prediction. How do engineers actually track these tiny deviations before they become massive structural failures? That realization naturally opens the door to the most intensive phase of the entire process. Geotechnical engineers simply do not need to wait until a tourist standing on the sidewalk can see a megastructure leaning. They are actively trying to detect structural movement long before the human eye ever becomes a useful measuring instrument. To achieve this, civil engineering turns into a highly precise physical investigation. During its construction and subsequent operation, the Burj Khalifa was subjected to an incredibly extensive survey and structural health monitoring program. Engineers rigorously tracked a massive array of physical data points. They constantly measured the structural strain developing deep within the concrete elements. They monitored the microscopic shortening of load-bearing columns and massive walls as the immense weight of the towering floors was incrementally added. They used advanced global positioning systems and highly precise survey systems to accurately track any lateral displacement and to verify any tilt-related observations. One particularly useful visual fact illustrates this level of intense engineering control. Exactly 16 individual survey points were permanently installed at the very top of the massive raft foundation. Their sole purpose was to measure actual foundation settlement with absolute pinpoint accuracy. The core concept driving this entire monitoring system is simple but incredibly powerful. The mathematical model explicitly dictates what the building should theoretically do. The actual physical measurements reveal exactly what the building actually does in the real world. The entire engineering question lives in the tiny difference between those two sets of data. The published monitoring work describes how engineers were constantly adjusting and calibrating their analytical understanding using the actual measured behavior. By tracking the exact position of those 16 survey points, they proved a strong, undeniable agreement between the original predicted behavior and the newly measured settlement. The monitoring transformed a terrifying physical risk into a completely controlled engineering process. But this incredible level of competence should not let the video end comfortably. What happens if a building does not have this level of monitoring, or if the actual measurements suddenly start proving that the structural models are completely wrong? We still have to confront the final, ultimate unease. We can now return to the central question introduced in the very first 40 seconds of this investigation. We must reveal the true physical threat. The enemy of a super-tall skyscraper is not simply settlement. The true enemy, the brutal force that actively destroys concrete and shatters glass, is completely uncontrolled differential movement. We can finally understand why our title is intentionally paradoxical. When we say a massive building is designed to sink, it absolutely does not mean that engineers actively want buildings to disappear into the ground. It means that engineers deeply understand that enormous structures and their gigantic foundations must inevitably interact with deformable ground. Because that physical interaction is unavoidable, the resulting downward movement must be meticulously predicted, evenly distributed, physically accommodated, and constantly monitored. A modern skyscraper does not actually need perfectly motionless ground to survive. It needs ground movement that remains incredibly close to the specific physical behavior that the structural engineers explicitly designed for. This is exactly why the Burj Khalifa is not used here as evidence of impending failure. It is the absolute central case study showing exactly how seriously engineers treat settlement, long before it can ever become a visible problem. If a foundation is correctly engineered, the building gracefully absorbs the massive compression of the earth. But the physical laws of nature are unforgiving to those who miscalculate. The margin for error in super-tall construction is incredibly narrow. When thousands of lives and billions of dollars are suspended in the sky, understanding the ground below is the only thing preventing a catastrophe. We can directly turn that profound engineering reassurance into one final, deeply unsettling question. The Burj Khalifa beautifully demonstrates that predicted, carefully controlled settlement does not automatically mean a skyscraper is failing. But what happens when the downward movement permanently stops being uniform? Let us go back to the terrifying visual from the very beginning of our story. Imagine one side of a foundation stays relatively stable, while another side actually moves significantly farther. What happens to the rigid internal columns? What happens to the delicate external facades? What happens to the critical load paths holding thousands of tons in the air? And at what precise point does a tiny difference beneath the ground become a catastrophic structural problem hundreds of meters above it? The Burj Khalifa is being used in this video strictly as an educational and analytical engineering case study. This video absolutely does not claim that the structure is currently undergoing any dangerous or uncontrolled settlement. Hypothetical failure sequences and visual analogies are used solely to explain the immense physical forces that geotechnical engineers actively design and carefully monitor against. This content is for analytical purposes and does not replace professional structural engineering advice. In our next investigation, we will answer exactly what happens when one side of a megastructure actually begins sinking faster. If you want to understand the hidden engineering systems keeping modern cities standing, subscribe to the channel. We will see you in the next deep investigation.